Welcome everyone to the CSE 234 Data Systems for ML Industrial Guest Lecture. It's a pleasure to have with us Dr. Jonathan Frankle. He's the chief scientist at MosaicML, which is one of the hot AI infrastructure startups that is doing a lot of cool stuff with developing more efficient algorithms for training neural networks, cloud native services for training large models and stuff. And Jonathan is also an incoming faculty member at Harvard in computer science. And he did his PhD at MIT, and there he published some fun stuff, including the lottery ticket hypothesis for more efficient training of sparse neural networks, kind of exploiting the properties of sparse neural networks for efficient training, which won the Eichler 2019 Best Paper. In addition to his technical work, he is also involved in policy-making challenges related to machine learning. So he's going to share with us techniques to make neural network training faster algorithmically. So, and protocol for the talk, Jonathan is happy to take questions during the talk. So feel free to post on the chat, or I guess, Jonathan, you will pause and take questions in between as well. So with that, it's all yours.
Yep, I will feel insulted if people don't interrupt me. So please interrupt me. So thank you so much for having me. I'll tell you about kind of the science we're doing at MosaicML these days. A couple of ground rules. The first is if anyone mentions the lottery ticket hypothesis, I'm going to ask them to leave. That is my dissertation. That is not my current work. And I hate showing up to conferences and having people go, oh, you're the lottery ticket guy. I hope eventually they'll go, oh, you know, you're a guy who did more than one thing. So, you know, just a ground rule from the beginning. Okay, so I'm going to try to cover 5 things here. We'll see how far we get. But number one is kind of, what are we doing? What is the problem we're trying to solve, and what happened? Then I'm going to talk a little bit about the science, because I'm a scientist at heart. What problem are we trying to solve? What does success look like? And why is this an interesting problem at all? I want to give some research context toward the end. You can kind of think of this as research problems for free. One of the fun parts of being in industry working on really bleeding edge problems is that I kind of look at what we do in academia and go, oh, that's all kind of boring and silly and esoteric. Here are some real problems that really need to be solved that I think would make better papers. And I will give them to you for free. Please just solve them and let me know what happens. And if we have time, I do want to talk about the business context at least a little bit. It's something I really didn't get exposure to during any of my formal education and kind of dropped into now. I've loved it. I found it really fascinating. And it's the kind of thing that I do want to try to share. So let's go ahead and dive in. And I want to start with the quiz here. So I'm going to ask everybody to get out a sheet of paper or a notepad or your email or something and just write down your answers to this. And I kind of want to get a sense, think in your head. I'm going to call on the poor folks who are kind enough to show me their video, because at least I can call on them. How much does it cost to train ResNet 50 on Imagenet to 76.5% top 1 accuracy? Dollars. So I see Alexander seems to have a sheet of paper out. Alexander, I'm curious, how much does it cost? I can't see it on the paper, unfortunately. So
can you read this?
It's very tiny. I'll ask you to say it out loud.
None of the above. I think it costs like 10 times more than the largest number on the screen.
Okay, perfect. Anybody else want to chime in? Anybody disagree?
I think it would be done in $10.
Somebody's looked at my slides ahead of time or something like that. It is $10. For anyone who has ever tried to write a paper in the machine learning world, you have inevitably had a reviewer say, can you do that on Imagenet? If you ever said it's too expensive, you lied to your reviewer. I'm sorry, the word is out. You can't get away with this anymore. I lied to my reviewers on this as well. I didn't know any better, but now I do. Stable diffusion. We all know stable diffusion. We've all seen the fun images on Twitter. Somebody else give me a guess. Anybody's on here. Chris, do you want to give me a guess?
I don't have a guess. Sorry.
It's okay.
This one we know is 100K from your website.
Oh man, people have done their research. Darn it, we should really stop putting these on the website. This is so unfair. It's about 100K. Actually, I'm told from our researchers it's now down to about 70K. As of today, that number keeps going down. So, it's getting better. How about a decoder-only language model to GPT-3 perplexity, assuming kind of chinchilla optimal, if anybody really wants the fine print here, assuming for the number of tokens chinchilla suggests you should do to get to GPT-3 perplexity. I know this is really technical, but people love to pick at the details here. Okay, we got somebody in the chat here. We got 3 million. Anybody else? You can
300K.
30K.
30K. We got some 30Ks. I really wish it were 30K. We're working on it. It's about 300K right now. If your reviewer
could you clarify whether the cost is in the hardware or also in the electricity?
This is just in the hardware. Let's assume the hardware includes electricity costs. You're paying a cloud provider, let's say. In fact, this is my list price. If you wanted to hire MosaicML to do this, this is what it would cost you.
Thanks, Ian.
It's a good question. And we can get into the details of where that cost comes from because it's actually kind of interesting. That's something we can get back to later. I wish it were 30K. We're working on it. We're getting there. Okay, this one's complicated. This is basically how much does it cost to pre-train BERT? But I have to put in all this other stuff because measuring whether you've pre-trained BERT successfully requires a lot of fine print. Don't mind the fine print. How much does it cost to pre-train BERT? Throw it in the chat. Let me know.
500.
500, we got a bunch of 500s. It's about 50 if you want to pre-train to BERT large quality. If you want to do it to BERT base quality, it's less than $20. If your reviewers ever asked you to pre-train BERT and you said, no, that's too expensive, you lied to your reviewers. That's bad. Don't do that. The answer is always the third option, Akshay. Yeah, you're right. This is kind of a boring quiz, but not trying to fool anybody. But the important part here is this stuff is not as expensive as you think. That's what I want you to take away from this talk.
You're unmuted, dude. You should mute it.
Some of this is hard work on our part. Some of this is just actually mere fact. That GPT-3 number is not because of speed up. That is just what we measured when we actually tried to do a baseline calculation. Stable diffusion, the same thing. This stuff is not as expensive as people think. And yeah, I yelled at you. You should be able to do this. If you go to composer.dev, it'll just link you to our GitHub repo. The code is there. You can go and do this today. So why? Training is really expensive. Training is really, really, really expensive. And it's getting more expensive. This is a plot that was popular last year. It came out in a paper where they were just kind of measuring for state-of-the-art models at any given point in time, how much did it cost approximately? So we'll talk about inference in a moment. But training whatever the state-of-the-art model is increasing exponentially. The number in the exponential is high, whatever it is. People debate that, whether it's 4x per year, 2x per year, whatever it may be. It is vastly outpacing the performance per dollar improvements in our hardware. That's for sure. And 400%, pick your number. And on the inference front, there's this big question of, well, don't you just train the model once, then use it for a bajillion inference queries? This is what Google said about the energy usage of their models for training versus inference. And they said about 3/5 goes to inference, 2/5 goes to training. Training tends to use more expensive hardware in terms of each watt, using fancier memory or fancier interconnects or things like that don't really show up in the power usage. It wouldn't shock me if the cost were 50-50. Training is a big part of this, even at big companies. This is one of the only numbers I've ever seen where a big company tried to compute this and record it. So there would be this. So I read in a history textbook about this thing called Moore's law and Dennard scaling. It hasn't been true in my lifetime, but I read about it in a history textbook. And they said this really cool thing where Andy Grove giveth and Bill Gates taketh away. That is to say, Andy Grove, the then CEO of Intel, CPUs were basically doubling in compute power for the same cost and for the same power envelope every 18 months. And our software was getting more power hungry and more compute hungry every 18 months. And it was this great virtuous situation where the same amount of money in any given year bought you a lot more in terms of what you could actually do. I would love to be there in deep learning. I would love to say that $1,000 today will still buy you kind of, wherever you are on the curve of state of the art next year and the year after and the year after. That's what I'd like to get to personally. To do that, we would need to decrease the cost of training these models by about 400% per year to keep up. And now suppose I gave you some large amount of VC money and said, go solve this problem. Now you're me. And the first thing you might do is you might say, well, let me build a chip. Why would you build a chip? Well, CPUs are good at doing basically nothing. They're good at doing general purpose computation. And the specific kind of computation we do in deep learning is pretty specific. It's matrix multiplies and vector operations. It would benefit from a different kind of hardware. So let's build a more special purpose chip that can be more effective at this. And everybody had that idea. That's happened. It's no longer cool to do this. And that happened. I will say it doesn't get you that far. That 40% per year that Moore's law gives you, that's probably a lie. But we'll be really generous to the people who are trying to shrink transistors. 10% in terms of architecture improvements. And I'm getting these numbers from, this is the cost of, approximately, A100 versus H100, at least when I last tried to price it out. From what I recall, November 2022 for the H100 is also pretty generous. That's probably more like, now June of 2023. But the annual improvement in performance per dollar between these two generations is about 16%, according to my numbers. If someone from NVIDIA watches this recording and you think I'm wrong, please go and give me some cheaper H100s. So, that's where we are right now. So what do we do next? Well, we build a compiler, right? Because the high-level operations we do may not be targeted properly to the low-level operations the hardware does. Let's target them better and try to take more advantage of this. And I'm not the only person to think of this. A lot of people are building really cool systems. At Mosaic, we love Triton, and we're talking to the XLA people, and we love our friends at NVIDIA and our friends at AMD who are building great libraries for doing this and for getting things to run faster. Compiler might get you 30%. And the way that I think about this is that if you look at PyTorch 2.0 and what they've promised in terms of basically a lot of compiler improvements, you're getting about 30% per year. That's, I think, a little bit overly generous. This leaves us a little bit short right now, assuming that these annual improvements continue forever, which they probably won't. But there's something really funny about all of these approaches, compilers, hardware, what have you. And I think it's especially pertinent for a class on systems. They all depend on executing the exact same operations in the exact same workload, bitwise in the exact same way, basically down to floating point non-determinism on the chip, and getting the exact same results. But there's nothing sacred about the math behind deep learning. Deep learning is approximate computation. We have mislabeled data. We are doing optimization that is not at all designed to work in these regimes. We're just hoping for the best. And we're doing all this other crap that we have no idea why it works, but it works. The high-level takeaway here is we are doing approximate computation, nothing exact. And so correctness doesn't matter. We don't care about executing the workload correctly. We just care about executing the workload such that it does reasonably well. To be more concrete, the goal of training or the goal of any approximate computing problem is to, reach a certain level of quality. That quality could be video encoding or what have you, depending on your approximate computing problem. For a neural network, that might be accuracy or perplexity or, doing well on some downstream metric. And you want to minimize some other quantity. In this case, doing it as cheaply as possible. This is our approximate computing problem. It doesn't matter how. There's no right way to do this. There is no right way to do this. The way that we're training our networks right now is naive and somewhat stupid. And that means that there are better ways to do this if we're willing to change the workload. It does violate one of our central tenets of computer science. If you take an algorithms class, before you even prove running time for your sorting algorithm, you have to prove correctness. You have to prove it actually sorts the list. I'm telling you, I don't really care if the list is sorted anymore, as long as it's mostly sorted most of the time empirically on most lists that you might get as input. I don't care about all lists. I don't care about being 100% correct. Good enough is good enough. That gives us a huge amount of freedom to go and do different things. Everybody with me so far? Are you at least, willing to give me the benefit of the doubt here, even though I'm telling you to throw away everything you were taught in a computer science class? If you were to do this for a SQL database, you would get fired. If you were to do this for a web server, you would get fired. In deep learning, nobody will know the difference if you do this. And my bet is that we will change the workload. We will change the algorithm to train these neural networks, and that will be how we will keep up and make things more efficient. And we've done it. ResNet 50 on Imagenet, this is our speed up work. 710%. It was a 7x cost reduction. This was 1 year by 5 researchers. This is not beyond the reach of any student at a university today. And here's our recipe. You don't need to take a screenshot or anything. It's public online. You can access the code. The things that are kind of in lighter font are things we tried that didn't make the final cut. The things that are bold are things that did make the final cut. The interesting thing about this is that just because you have a bunch of different ways to improve training individually does not mean they get along well together. That's not a shocking statement, but it's something that we encounter every day. The metaphor that I love is drug interactions. You may have 2 medications that really, really help you individually. They may kill you if you take them together. And understanding those interactions is a science, and we're trying to understand that. As our CEO put it, he's a hardware guy, so he put it pretty well. And he's built machine learning chips. Would you rather invest 200 million into a new computing architecture and maybe get 2x, or less than 5 million? And I would say it was closer to 1 million, and get 7x with better algorithms. When I make the case to policymakers who want to invest in national compute infrastructure, I tell them that each dollar will go further if they invest in better ways of training models than it will if you just buy more GPUs. And we did it again. We've done it for BERT pre-training. Cool. 3x cost reduction. We did it for image segmentation, 5x cost reduction. And there's a lot more where that came from. We're now working on these two models, and you should expect a lot of substantial cost reductions in the next few months. That BERT number will be coming out next week. So, don't tweet about it, but it's coming. So I want to talk. Oh, go for it.
Sorry to interrupt.
Oh, go for it, please.
What's the data set that you used? Kind of like a standard data set, or was it kind of like, are these results, like when you talked about how these different techniques interact with each other, is there a function of the data set that will influence this result?
You asked the killer question right away. So ResNet 50 on Imagenet, Imagenet is Imagenet. For BERT pre-training, we tried a couple of different pre-training data sets. We like to use C4. That tends to be a good data set for this, but we saw similar results in other pre-training data sets. To a large extent, language is language. Some data sets are better than others, but we haven't seen differences in speed up. For DeepLab v3 on ADE 20K, we then did try to transfer this recipe to another image segmentation benchmark. We had to, there was one thing that wasn't compatible for a specific reason, I think a resolution issue. We got I think a 2x or 3x right out of the box. Then when we fixed one or two things to account for the fact that the data set was very different in size, we got, I think, up to 3x or 4x. So it wasn't a perfect transfer, but it was good enough that if you were a customer, you would be very happy with that. But this is something that scares me every single day. What if we overfit? Other questions, other feedback, go for it.
I have a question, sorry.
Yeah, go for it.
Yeah, I was thinking the techniques that you're mentioning, I'm just thinking, will the research community, be able to do this when, benchmarking models, right? Because when you're benchmarking different kinds of models, you want you want almost everything to be the same for all the models and still be able to, show comparable results. So even though this might help in the industrial setting where, you're going to try different things for a specific model and, 8 out of those 10 things work. When you're comparing models, you have to keep everything the same. And then when you do that, then, you have to keep things very simple, right? You cannot overly complicate, things like blur pool or, the different methods that you mentioned here, right?
So let me ask you a question back. A traditional ResNet 50 on Imagenet uses, for data augmentation, you do random flips, random crops, and rescales. You also include batch norm. You also include residual connections. You also use cross-entropy loss. Aren't those pretty specific choices as well? Why is that a vanilla baseline but not this? So really the reason I'm asking this is essentially, if you told me that you took the ResNet 50 from 2015 and improved it on Imagenet, who cares? Nobody's using the ResNet 50 from 2015. That's not a hard benchmark to improve upon. I want to see you improve upon this. That's when I consider your method to actually be good. You took a really hard baseline and you made it better. So as far as I'm concerned, it's really just a matter of how you set your baseline. And if you're setting a wimpy baseline from 2015 that you call vanilla, I call a waste of time because nobody cares if you go and beat up on a 7 or 8 year old benchmark. That's my take on this. I tend to be very opinionated on these things, and I'm sure you're telling.
I actually don't know much about the CV world. I'm more of an NLP person, but we basically, whenever there's something, you compare 9 to 10 different language models, and things like learning rates and scale schedule or these kinds of things can drastically change how one model behaves versus the other, right? So that's why the doubt actually.
You should be comparing against the very best version of any model that you have. When we get to actually, I'll skip ahead momentarily. There are 3 cardinal rules of the game. The third cardinal rule is you have to optimize your baselines with as much compute as you use to optimize your final model. Otherwise, all you're doing is measuring how much compute you used on a particular task. It's expensive and it's not fun to optimize a baseline, but we've often gotten up to 2x speedups from optimizing the baseline. And then the improvements I've shown you are off of that optimized baseline. That's, I think, how you do good science. The NLP community has terrible scientific practices. As Ashish Vaswani once explained it to me, I think, it's not about how you made the cake, it's about how it tastes. And that includes doing hyperparameter search on your test set. and picking the max point that you get on your test set, not picking the final model, not running multiple replicates, but picking the best replicate, that's not good science. So the way that I think of good science is you have to optimize your baselines just as much as your final model, and then you have to compare across multiple replicates. And not, if you're going to cherry pick your model, cherry pick on a validation set and try it on a test set. So, we can talk about bad empirical practice. This is my preference personally.
Sounds good. Thanks.
And yeah, the NLP community does have terrible scientific practices. It's also accomplished remarkable feats of science over the past few years. So, you don't need to have amazing scientific practices to move the field forward, but I think we'd move forward a lot faster and be more confident in what we did if we had better practices. We also have a question, how much of these improvements are specific to a task or data set, not generalized? Okay, we chatted about this a little bit. Awesome. Other questions, comments, or complaints? Yeah, I do have.
Can I ask a question?
Yeah, go for it.
So I'm assuming that there's accuracy trade-offs to this approach. What accuracy reduction are you comfortable with? And is that dependent on the task or not?
There are no trade-offs with this approach, and I'll show you in a moment. There is no accuracy reduction. In fact, there are accuracy improvements in a lot of cases. Our framework takes that into account, and I'll give you that in a moment. So give me about 30 seconds. So let's push forward a bit. Here's the game that we play. If you want to play my game, you have to play it according to my rules. My game is we have to reduce the time or money necessary to train a network. I want to emphasize that one more time. I even highlighted it earlier in the slide, time or money. I don't care about flops. Flops are made up and flops are a lie. I don't care about sparsity. To criticize my own dissertation, I don't care about sparsity. Sparsity is made up and sparsity is a lie. I care about how fast it goes on a real piece of hardware that somebody can use today. It's really easy to hack sparsity or flops to make numbers look good in a paper, and you can get it published that way. That's nice. But your work is useless unless you've actually shown that it speeds something up in practice or reduces the cost or energy usage or pick a real metric that you can measure about an end-to-end system. So I want to emphasize that. Rule number one, you can't present people with a trade-off. That means the cost of inference cannot increase. If one of my customers has to weigh whether it's worth trying out my fancy new model because they have to figure out how much training versus how much inference they do, they're not going to do it. It's going to be too much of a risk. You can't increase the cost of inference. Number two, the hardware platform and software stack are fixed. Switching from an A100 to an H100 is not an algorithmic speedup. That's NVIDIA's speedup, not yours. You're not allowed to claim credit for it. Switching to a new CUDA version or new PyTorch version, not a speedup. You have to earn it yourself. Rule number three, you have to optimize your baselines. We already went over this one, but I'll say it one more time. Everybody repeat after me, at least in your head. I promise from this day forward, I will always optimize my baselines. That is the number one thing when I'm a reviewer that I reject papers for. I can tell when you have a bad baseline, and I will come after you for it. I want to give one example of a speedup method. This is not, the world's greatest speedup method in terms of actual speedup, but I think it's interesting and shows a little bit of the art and science of doing this. This is a method called Selective Backprop. If I simply told you the name Selective Backprop, I'm guessing 75% of the people here would write down the method without needing to know what it is. You have a neural network. I hope everybody here is familiar with neural networks. You have some images that you're running through the network, and you get some loss values on the forward pass. Now, let's be approximate. Let's take a leap of faith. These two examples in the middle, they have relatively low loss. That means A, the network knows them pretty well, and B, they're going to have pretty small gradients. So what if we drop them and only do the backward pass on the two examples with high loss? This could completely screw things up. We have to actually run the experiment and see what it does to accuracy. But the backward pass takes about twice as much time as the forward pass. So if we cut, half off the cost of the backward pass, we've cut a third of the cost of training. That would be huge. We get these speedups in 5% and 10%. There's only one thing I can think of that is a 1/3 reduction in the cost of training. That would be huge. Now, unfortunately, you can't do this in practice in PyTorch. AutoGrad won't let you change the shapes of the activations once they've been created. And your answer can be, well, why don't we modify AutoGrad? And my answer is, well, I don't want to maintain a separate fork of AutoGrad. So you're kind of out of luck if you want to do this in a practical way. So there's a solution to this. You do 2 forward passes, one to compute the losses, then you figure out which examples to drop, then you do a second forward pass only on the examples that you're going to use and a second backward pass just on those. This will work in PyTorch. This comes with overhead of doing that extra forward pass. That costs you something. It ends up basically cutting your speed up in half. And it ends up basically whittling away so much that we didn't find it to be worth it, because this does cost you a bit of accuracy left to its own devices. I'll get to why that isn't a trade-off in a moment. But for now, it doesn't end up being worth it like this. So we have to be approximate again. What if on that first forward pass, remember, we're not trying to get the exact loss. We're just trying to get an ordering of the losses of the examples. So we don't have to be exact here. What if we forward propagate low resolution images instead? That'll cut the cost by, that'll cut the cost of this extra forward pass by 75%. And we can even batch it together over a bunch of mini batches to do it even better. Then we're going to get the wrong loss values, but that doesn't matter. As long as the ordering is roughly preserved approximately, we're in good shape. And then you can do the usual thing where you do the second forward pass and the second backward pass. What I love about this is it requires 2 levels of approximation. One, because the method is using approximation to speed things up, and another because you're using approximation again to correct for a systems level problem that you can't solve. This isn't the thing that I'd recommend you do today, but it's a great example of the kind of work we do at Mosaic. Plenty of papers have proposed the original version of this and shown a flop reduction. We actually got a real speed up out of this, but it took a lot more science and engineering. So let's see, we got a question. There's some work about finding hard and easy examples. We've never found finding hard and easy examples to actually work. Curriculum learning is the most obvious thing that never works. I've never seen an example where any curriculum learning technique has actually worked consistently in deep learning. I would love to find that technique. If I'm wrong, tell me. I have a set of benchmarks that I would want to see success on before I'd believe it's really true. I've never seen anything work in practice, unfortunately, because it should work. Okay, I want to keep pushing. So I'm going to just skip over these methods and tell you how we evaluate success and why there's no trade-off. Why even when a method costs accuracy, there's no cost. So the simple answer here, how do you know when you've succeeded, when a method is worth using? You get a network that's just as good in less time or money, right? If you were moving from the A100 to the H100 and you get a network that's just as good, you get the same network and it's cheaper in performance per dollar, life is good. NVIDIA is done. But there's a risk here. Just as good gets really complicated when you're doing approximate computation. What does it mean for 2 things to be just as good? One risk here is in my own home literature of pruning. We used to say that we could prune models by up to 90% while still preserving accuracy. But it turns out when we did that, they were actually getting more biased. They were preserving accuracy, but on different examples. That's something we weren't measuring. Oops. So you do have to be a little more careful in these circumstances. We spend a lot of time worrying about this. But problem number 2, what if you can't get anything just as good? What if I told you that the selective backprop method gets you a 33% reduction in the cost of training, but you lose 1 percentage point of accuracy? Worth it or not worth it? Anybody think that that's totally worth it? You should do that? It's only 1% of accuracy. Anybody? Anybody think you shouldn't do it? That's 1 whole percent of accuracy? The answer is it depends. It's a trade-off. If you're Facebook, that 1% of accuracy is billions of dollars. If you're on an AV, that may be totally worth it because you just need the damn thing to run. So here's how we evaluate success and make sure there's no trade-off. This is this thing I invented called the Pareto Curve. I didn't invent this. I really didn't invent this. It's something I never actually see in machine learning papers, even machine learning systems papers. It is something that you should always see. People are always doing these incomparable comparisons, like the baseline was this much faster and lost this much accuracy, and I was that much faster and lost that much accuracy. Therefore, I'm going to bold my line, and mine is better. They're incomparable. So how do we make things comparable? Well, here's my baseline. Let's suppose this is ResNet 50 on Imagenet. Training time is 3 hours and 33 minutes. Model quality is 76.5% top 1 accuracy on Imagenet. Suppose I give you this point right here. I want folks to tell me, raise your hand or in the chat, would you take this? Suppose quality captures everything you care about. It captures bias if you care about bias. It captures accuracy if you care about accuracy.
Jonathan, I already ran this question in the first lecture of my class.
Awesome. So everybody should know. Somebody tell me. Somebody just shout it out. Will you take this or not?
Yes, it's faster and better.
Of course. Why would, if I had this, I'd be ecstatic. Even this you would take, right? Like it's at least faster. What about this? You don't have enough information, right? It depends. You don't know. So, and what about this? It is better in one axis, but worse in another. Who knows? So yeah, and really, thank you so much for apparently setting me up. This is beautiful. I don't even have to teach what Pareto curves are, and I feel like I have to teach that to machine learning folks all the time. Even though we should all know it. So you need more info. So does anybody know this baseline point right here, this blue point? I trained it for 90 epochs. Does anybody know why we trained ResNet 50 on Imagenet for 90 epochs? Anybody want to shout out and tell me? There's a really good reason. Not 89, not 91, not 200, not 5. Anybody? Because Kai-Ming trained it that way in 2015. That's why we trained it for 90 epochs. And in fact, there's this really fun thing you can look at. Our Imagenet scores have been getting better and better and better over time with vision transformers, all this new fancy stuff. Something else has happened. The number of epochs we train on Imagenet for has crept upwards along with accuracy. It became 150, then it became 300. Now some people train for 600 epochs on this. But the answer is really, there's no right answer. We could train for 45 epochs or 125 epochs or 1,000 epochs. And really, our baseline is not a point, but a curve. It sounds like this is already obvious to you all, given that you've learned about this, but your baseline is not a point. This whole curve is my baseline. My baseline is what is the trade-off between the amount of time or energy that I spend on computation and my quality. And now if I show you this point, how many people think that this point is better? Yeah, of course it's better. It's a better trade-off than I could achieve before. For at least this amount of training time or this amount of cost, I'm getting better quality. This is great. But also, this is kind of a lie because my speed-up method is also a trade-off curve. I can try that same speed-up method for lots of different training times. This is how we measure at Mosaic. We look at two Pareto curves and ask, did I improve the trade-off between training time and cost? This is why I can promise you that none of the speed-up methods we ever propose cost you accuracy. Because if they do cost you accuracy, you can just train for longer. And if it's worth it, you'll see that point above my baseline on the Pareto curve. So we look at this, and I'll show you some real Pareto curves in just a moment of what things actually look like for us. They're a little more complicated than this. They often cross, but we'll get to that. Any questions, comments, or complaints beyond that, you all are bored because you've already learned all this?
Quick clarification, Jonathan. Are you actually training all the combinations of these models to get the Pareto curve, or are you estimating the curve?
So we are training, for every single training run length, we have trained this model. Okay, we don't try every combination of speed up methods. We are a little bit greedy about it, and we have some heuristics for choosing them because the space is way too big.
That's why. That's why I was wondering, because there might be too many combinations to try to get the curve.
Oh yeah, it's a lot of intuition. We're slowly developing science around this. Okay. If there are 5 or fewer methods, we can often build our way up. When we got to 36 methods for Imagenet, someone very talented on our team did a greedy search of the space using his best intuition and got to a good recipe. It's probably not optimal, but it's pretty damn good.
Got it. Okay, thanks.
There is a trick if you want to get this Pareto curve more efficiently. We have a blog post, one of our intern projects. Cyclic learning rates actually work quite well. You need to be careful how you use them, but you can train with cosine decay and stop, and then go back up and train with cosine decay a little more and stop. And in this way, you can get a full Pareto curve without having to, spend a quadratic amount of compute in order to get every single length here. There are trade-offs in that, but it is useful because in the real world, it turns out nobody tells you to train for 90 epochs. You don't know how long to train. Okay, so I want to keep going if there are no other questions here. Also, the speed up numbers that I quote you are this point. For the same quality, what is the minimum cost? It's a way to distill one Pareto curve, which has a ton of information into one point, so I can put it in a pitch deck and try to get money. Or so I can put it on a slide and convince you I'm cool. So I want to talk a bit about composition. This is the killer. That is the question you just asked, Arun. Composition. So the way that I would define this problem, and this is an awesome, fun scientific problem. Under what circumstances can 2 or more methods be combined to produce an even better trade-off? And in our ideal world, we'd see something magical like this, where you get some kind of vector sum or something nice happens and the 2 methods combine their best qualities. If only. Have you all learned about Amdahl's law yet? Is this an old hat, or is this, okay. Oh, perfect. I don't need to explain to you Amdahl's law. What I'm actually writing here is the corollary of Amdahl's law, which is that repeatedly optimizing one component of a system leads to diminishing returns. If you reduce the cost of backprop by half, and then you have another method that reduces the cost of backprop by half again, you're getting less out of that second method than you did out of that first method. Early in the company, we actually had 2 methods, both of which attacked backprop, each of which provided an accuracy reduction, but enough of a speed up to be worth it. But when you combined them, they were actually worse than the original baseline because they both ate into that. They were both speeding up using the same thing, but they both cost you a little accuracy. And the second one cost you more accuracy than the first one. So Amdahl's law has been a really useful kind of framework for us. The other thing is this idea of a regularization budget. And what I mean by this is as follows. I would challenge anyone in this room, first of all, to define regularization beyond I know it when I see it. But my best definition is anything that kind of makes the training task harder in order to help you do better on test accuracy. That's kind of the shape of the curves you look at. Other definitions can include capacity control, like weight decay or any kind of L2 penalty on your model is typically a popular form of regularization to keep the model from overfitting or developing weights that are too big or too specific. So the thing is that there are a lot of different ways to regularize a network or things that function in that way. For any given amount of training, you can only tolerate so much regularization. If you regularize too much, the model won't learn. If I told you had 90 epochs, you should only apply a certain amount of regularization to kind of optimally make the task hard. As you train for longer, you can tolerate more regularization. Now, there are a lot of different ways to regularize a model. You can use weight decay, you can use data augmentation, you can use sharpness-aware minimization, this new optimizer. And the trick is to make sure that you're applying your regularization methods that cost you the least first. Sharpness-aware minimization is a new optimizer that's really cool. It allows you to reach similar accuracy in many fewer steps. The cost is that you have to do 2 backward passes. So it's a huge penalty in order to do this. There are other regularization methods that don't cost you anything, and you should apply them first. And I'll give you one example. There's this really weird regularization method called cutout, where you just feed the image into your network and you gray out a patch of the image. And supposedly, maybe this makes the task harder, the network has to work harder. This ends up, if you train for long enough, improving your accuracy. Now, in your ideal world, you also don't have to do any computation on that missing part of the image. Those are convolutions you could skip, but unfortunately, there's not a non-rectangular convolutional kernel. We invented this new version of the method called callout, where you just drop entire rows and columns, and you can do this to the image if you really want, which lowers your resolution and actually gets you speed up from regularization. This is something we would go to first ahead of cutout. And eventually you work your way to the regularization methods that are actually penalties on training time, and you deal with the trade-off. But being careful about how you regularize is really valuable. There are all sorts of other drug interactions that happen, and also there are other bottlenecks in the system. Your GPU is your most expensive resource on the system, but if you were to train ResNet 50 on Imagenet on AWS on their A100s, you'd actually be bottlenecked on CPU. Amazon chose a pretty wimpy CPU to go with its A100s, and you'll be data loader bottlenecked on doing data augmentation, and you won't fully utilize those A100s to the extent that you could. That's really annoying. If you speed up the model enough, you'll get data loader bottlenecked again. If you speed up the backward pass enough, you might get bottlenecked somewhere else. In a lot of cases, you can get memory bandwidth bottlenecked on the GPU memory if you're doing very small operations that you haven't fused together with others. There's a lot of work here to eliminate bottlenecks that show up. Any questions on composition? This is one of my favorite new scientific problems that I love to play with. There are just so many combinations and exciting things happen when you have these methods interact. It's really fun. Makes for a great workshop paper. So I want to show you some actual Pareto curves. This is our real ResNet 50 on Imagenet Pareto curve. It's not quite the idealized Pareto curve I showed you before, but it is, quite nice. You'll see a bunch of baselines here. The NVIDIA HParam baseline. That's kind of if you go to the NVIDIA HParams library, this is what, or the NVIDIA examples library, this is what you'll see. This is basically the 2015 recipe. Yeah, we crushed that, but who hasn't crushed the 2015 recipe? But you can also see some other examples of FFCV, which is a recently released library for speeding up the data loader, TIM, which is a popular computer vision library, and we're able to get some pretty significant speed ups over those too. One cool thing to note here is you'll see actually 3 different recipes, mild, medium, and hot. We stole that from Taco Bell. Please don't tell them or have them sue us. But the idea here is that the optimal recipe for different training lengths is actually different. These generally vary in the amount of regularization. If you're going to train for longer, you can regularize more strongly. It'll cost you accuracy in the beginning, but it'll be worth it in the end. You can also see we hit almost 81% top 1 accuracy here, or I think more than that. Your ResNet from 2015 hit 76% accuracy all the way down toward the bottom here at the boring part of the curves. So again, for that poor person I beat up about how they should use real baselines and not baselines from 2015, beat up on these baselines. Show me you can improve on this, and I will be really excited and put it in the library. Questions about this Pareto curve? I love seeing this real data. It's messy, but it's kind of interesting. Here's a Pareto curve for image segmentation. This optimized baseline is actually already a 2x speed up over the typical baseline that's out there for this particular benchmark. And we got not only a lot faster on that baseline, but also we got way more performance out of it than had originally been gotten. Almost to the point where we kind of wondered whether you really need fancier architectures for this. And here's for BERT. This is a nice matplotlib plot because we haven't done the final graphics yet for our blog post. But BERT, we're looking at a nice solid speed up here as well. And we're measuring on glue downstream performance. We're not measuring on the masked language modeling accuracy. That tends not to correlate that well with how it actually works when you do transfer learning. So we're focused on the real world use case. Questions or comments on any of this, or complaints? You're allowed to yell at me as well. I yelled at you. It's only fair. Okay, off topic. How much of Mosaic's budget goes to benchmarking? Not that much in the grand scheme of things. People are way more expensive than GPUs. But all of our computational budget sure goes to this, except for that which we sell to customers. But yeah, this is expensive. But the value for our customers of reducing the cost of training GPT-3 by 10 or 20%, that's another month of runway they have, or that's health insurance for their employees or what have you. So this stuff does really matter and provide a lot of value. Other questions?
Hi, I was wondering, in all these plots, how do they differ in models complexity, like Mosaic versus other baselines that you're showing?
What do you mean by complexity?
Like the memory of is it reduced by weights or?
So the computation is reduced a bunch of ways. In some cases, we literally made the operations faster. We fused a layer norm with a matrix multiply in a way that avoided a memory bandwidth bottlenecked operation. In some cases, we actually reduced the number of update steps that were necessary. Regularization does that. It makes, each step gets a tiny bit more expensive, but we need many fewer steps to get to our final conclusion. In some cases, we actually increased the number of steps, but made each step much cheaper. So it's not a clear apples to apples, but it's a little bit of everything.
But then how do you choose which baseline to compare it?
We compared to whatever people were doing prior to this. As long as inference cost didn't go up, we're happy to beat up on any baseline we want. But that inference cost restriction actually matters. I can't just train a model that's 10 times as big and say I did better.
Thank you.
Okay. I'm still not sure about the scalability in terms of tasks. How does one ensure the speed up gains can be replicated across data sets and tasks without having to redo the whole process? You take the final recipe and compare it to the baseline. You don't have to necessarily search for a new recipe. The goal isn't to find the optimal recipe for each task. The goal is to find a recipe that seems to provide consistent speed up across a wide range of tasks. Finding the recipe is expensive. Evaluating it on a bunch of tasks is not that expensive because it's one training run per task or a handful of training runs per task. So you don't have to redo the whole process. If you do end up finding that something doesn't work on another task, you need to go back and simplify your recipe. You may have made some decisions that were way too specific. This is also a reason why we tend not to do too much hyperparameter tuning. Once we've picked our speedup methods, we try to keep things as generic as possible, because that's how we found ourselves getting into trouble. When we've picked a really, really specific rate for something that doesn't end up scaling from task to task. The real proof is in, whether it actually works for a customer. So, the real proof is in, did somebody actually benefit from this? We've got a hand raised, go for it.
What are the ingredients of these recipes?
Sorry?
What are the ingredients of these recipes?
You can go online to our examples repository. I'll flash the link in a moment. They're all online. We've got blog posts about each of these. You can go and take a look at them all. But these are everything from little data augmentation methods to different optimizers to different ways of doing downsampling in the network to, it's really kind of anything and everything. The company is actually called Mosaic for this reason. The idea of assembling a lot of small pieces to make a bigger picture. It's something that we tend not to do in the research community. We love to isolate individual methods and say, my thing is better than your thing. We tend not to try to put the pieces together and see how all the things work when you combine them. That's a lot of what we do.
What is the company actually trying to do? Are they trying to sell cheaper versions of already popular models with big hype around them, or are they trying to provide like an all-purpose? Okay, like let's say that a completely new task were to come out that nobody has ever heard of. Would Mosaic have something to apply to that, or is this just for making GPT cheaper?
So there are two answers to this question. What we actually sell is compute. Customers come to us because we have a fully integrated stack, where if you use our GPUs, you use our orchestration software, and you train our versions of these models, you're going to do it way cheaper and way more easily than if you try to roll it all on your own with some cloud compute that you bought from, Amazon. So we actually make money off of compute. These recipes are just one way of helping people to make sure that by using our compute, they're going to get further than if they use somebody else's. The nice thing is that everybody wants to train GPT-3 right now, so we really only have to focus on one model. Anybody who doesn't want to train GPT-3 wants to train Stable Diffusion, which is great. We only have to focus on two models. That will inevitably change, and our goal as a research team is to keep up. We work really hard to stay on the very bleeding edge, so we're ready to get things integrated as soon as they come out, including new models and data sets.
Is the goal AGI, or is the goal just to capture these couple of top hyped models? People who want to train 10 to 20% cheaper versions of them, or is the goal to provide compute to anyone who wants to train anything faster than what the current baseline is?
The goal is to help people get work done and build something that's useful to them. I think AGI is stupid and a waste of time. With no offense to my colleagues at OpenAI, I think that's all hype and dogma. I prefer building tools that make people accomplish things they couldn't do otherwise, or help people do things more efficiently.
Also, hype behind them, or general tools?
Specific tools. I don't really care what the tool is. If you told me there was AGI and you told me that we could train AGInet to do it, I'd happily, build that. I think AGI is, you don't want to get me started on AGI. That's a whole other conversation. I will also say, if you ever interview at Mosaic and you mention AGI during an interview, it's an automatic out.
I guess I'm out.
You're already out. I'm sorry.
Yeah.
But it's important to me that our team is focused on delivering, useful things to people here and now, not on playing around with, ethereal nonsense that isn't even well defined. Let's see, we've got a question here. If you're allowed to share this, what are the tough questions from VCs and other financiers that Mosaic anticipates having to answer in incoming series rounds? The questions are always about, how many customers are out there and how much can you scale this business? None of the questions are that creative or that specific to us, but they're always fair questions to ask any business, especially one in our stage. But I wish there were some special magic question VCs could ask that would automatically knock us out. If there were, I sure wouldn't tell you on a recording. But usually it's all about just what is the nature of your business. Other questions folks want to get in? I know we're already running short on time, so I'm talking fast to make sure I address everything. So
I had a question regarding the curve saturations. Like there can be cases where you're training for a long time and suddenly you see that one saturates while the other starts growing. So have you seen those cases, and then how do you here, yes, you see it after like 250, right? But in some cases you might see it after like hours and hours of training. So
is this kind of the grokking phenomenon you're describing, where like the loss curve kind of stays flat and then suddenly gets better?
Yeah.
It's honestly not a phenomenon I've ever encountered in practice. There are a lot of fun phenomena that you can get to happen in academic settings if you want to. I'm much more interested in what happens in practice, and I've never seen it happen personally.
Yeah, my question was more on like, then do you choose the one that's like better in the earlier stages but saturates, or the other one which is like suddenly shooting up later on?
So the answer is we choose both. We'll choose different ones depending on how long you're going to train for. Now, you have to be careful. You don't want to have a different set of hyperparameters for every single length. We kind of like this having one recipe for short runs and one recipe for long runs. And generally, it's easier to segment, like, whether a customer is trying to do a really long run or a really short run. That's so kind of the medium and hot are the ones I recommend. The only reason we have a mild recipe here is because MLPerf, this kind of nice industry benchmark, asks you to train to, I think, 75.9% top one accuracy, which you can see is kind of way off to the left and isn't really even a good number, but that's what they asked for. So we created the mild recipe to focus on that because, we need to show off our stuff.
Okay, got it. Okay, thanks.
We've got a couple questions coming in here. Maybe off topic, but saw the post about PubMed GPT. So PubMed GPT is a language model we trained with some colleagues at Stanford just on the PubMed corpus, which is a bunch of medical publications. The goal was to understand do you really need a general model like ChatGPT, or can you really train a bunch of small domain-specific models? And we got pretty fantastic results on just training a 3 billion parameter model. So, 50 or 100x smaller than GPT-3 on a lot less data for a lot less cost, and still getting great results in a domain-specific context. We collaborate with research groups to some extent, but it's really, at the end of the day, I need to justify a business case for everything. This is part of why I also have that academic life, because in my academic life, I don't have to. But in the business context, at the end of the day, everything does come down to dollars and cents. Can you go into the startup specific business context you mentioned at the start of the slides? So we've got 5 minutes left, and I may take a quick show of hands of the people who are brave enough to turn on their video. We have two options here. We can either talk about research questions for free, really cool, exciting ideas that came up, or we can talk about business for a little bit. Raise your hand if you want to talk about cool research questions that have come up. Okay, we got 3 hands here. We got 4 hands, 5 hands. Okay, raise your hand. Okay, hands down. Raise your hand if you want to hear about the business context. Okay, we got some hands. Okay, we got a bunch of hands here. Oof, this is about 50-50. I'm going to try to be quick and talk about both. So the business context, very briefly, I think I already mentioned the core part. We sell compute, not models, and not speeded up methods. It turns out selling efficiency is really hard. You have to convince someone they should spend money to save money. That's not a winning proposition. Telling someone they can simply do the thing for cheaper is a winning proposition. So bundling the compute with the efficiency is the way to go on that front. And we found that to be a much more winning formula. Building a business in this economy and in this startup world is really crazy and a lot of fun. Are there any specific questions folks have about the business side or things they want to know? It's something I certainly wish I learned more about. Okay, we got a hand raised. Go for it.
Yeah, do you have like your own servers, or do you just use like AWS or something?
So the answer is yes.
Like, how do you sell compute is what I'm trying to ask.
We have some of our own servers. Maintaining your own servers is a nightmare. A100s, it turns out, die very often. These are chips that are being run at insane power levels with insane heat. And so they die quite frequently, and it's a pain in the butt to maintain your own GPUs. So we mostly sell GPUs that we get from a third-party cloud vendor. And a lot of customers will often come with their own compute, and we'll just charge them a little bit of a value add to manage that compute and help them use it efficiently. Let's see, we got a bunch of questions here. I'll try to answer one of them quickly. Who are your customers? You can go to our website and check that out. We've got a bunch of logos up there. They change frequently, and I'm less customer facing, so you can check that out on our website. For our competitors, we have lots of competitors. There are lots of folks who tell you they can train a large language model for you efficiently. And all those companies are our competitors. Our competitors are the fact that you don't need to train a language model at all, like our friends at OpenAI or Anthropic or Cohere or what have you. The world is big enough for all of us, I think, because this is a big market and there's a lot of work to do and a lot of people who need help. Moats are complicated. I don't really like talking about moats because I think it's kind of a silly concept. At the end of the day, as long as you're delivering value to customers and you're growing your business, you don't worry too much about your moat. You just want to help make your customers successful. That's really, if I had to give you the one secret, it's love your customers and make sure they succeed. If they succeed, you will succeed. I think we're largely at time. Any other questions folks want to try to cram in before we wrap?
So Jonathan, quick question. From the standpoint of a user of this service, do they not need to do any more hyperparameter tuning? Because the compost techniques implicitly regularize, they do learning rate adjustments and stuff like that. And you're already building a Pareto curve. And a part of hyperparameter tuning is to build that Pareto curve. What is your take on that?
You're probably going to have to do some amount of hyperparameter tuning in any context, but our hope is that we've squeezed out a lot of the hyperparameter tuning pain that you would need to do, especially in large language model contexts where I don't tend to see very big hyperparameter differences between what's optimal for, say, C4, what's optimal for the pile, and what's optimal for PubMed. So we're doing a lot of hyperparameter tuning right now on good learning rates for training GPT-3, because I think that's an underexplored area where there's some opportunity to improve things, but I sure hope it doesn't differ.
Okay, sounds good. Okay, so we are at time. Let's give Jonathan a round of applause for the very energetic and exciting talk. You covered probably more questions than any guest lecturer I've ever had. So kudos to you.
I'm sorry that I talked fast, but I want to make sure that we make the most of our time together. If you have any more questions, My email is jonathan@mosaicml.com, so I'm really easy to find.
Okay. Thank you, Jonathan,
Awesome.
and thank you to the audience for joining. Take care. Bye. I'm going to stop the recording here.